everybody. Welcome back to Environmental Organic Chemistry with Dr. Lisa. I'm having a great day. How are you? I know it's exciting. Yay, it's time for Environmental Organic Chemistry. So this is an example problem that's actually based on a midterm exam that I gave a few years ago. So it's called Practice Problem 3-Phase Partitioning up here. And so the idea is that as just a very rough first approximation, you could think of a sewage treatment plant, a typical sewage treatment plant with secondary treatment, as a system with about a liter of octanol for every 20,000 liters of water and about 200,000 liters of air. And, you know, that amount of air is because the air is flowing over the treatment plant, right? And in most treatment plants, you're bubbling either air or oxygen through the water. So effectively, it's a large volume of air. And 1 liter of octanol for every 20,000 liters of water doesn't sound like a lot, but octanol is a very strong sorbent, so yeah, it actually absorbs chemicals pretty effectively. So the question that I gave in this midterm exam was to take these 3 chemicals, phenanthrene, which is a PAH compound. You can see here I chose these chemicals very carefully. Phenanthrene is a typical hydrophobic organic pollutant that you get from the combustion of all different types of carbon-based fuels. Tylenol, you all know, is an over-the-counter pain reliever, and the active ingredient is called acetaminophen. Chloroform is formed during the water treatment process. If you're going to use chlorine for disinfection, it's a very common disinfection byproduct, so that makes a lot of sense to think about that. And then 2,3,7,8-TCDD, or 2,3,7,8 tetrachloro-dibenzo-P-dioxin, is a very toxic, it's the most toxic of the dioxin congeners, and so it's a large hydrophobic chemical. And so we're going to think about how it's going to behave, how all 4 of these chemicals are going to behave in the wastewater treatment plant system. So you're asked to calculate the partitioning between the air, the water, and the sludge. And anything that is in the air will volatilize away. Anything that's in the water will leave the plant with the effluent and go into the receiving water, where it could be a problem. And whatever is in the octanol phase will end up in the sludge, which, you know, management of sludge from wastewater treatment plants is a whole big complicated issue in and of itself. And what do you do about these nasty chemicals that end up in the sludge? You know, it's tricky. Okay, so the calculations are pretty straightforward here. It's based on 2 master variables, your Henry's law constant, your dimensionless Henry's law constant, right? So I've shown that here. I've given you the Henry's law constants for these 4 chemicals. Here I've just converted them into, instead of log of Henry's law, I've converted them into just straight up dimensionless Henry's law. And here's log of KOW, and then I've converted that into actual KOW. And so you can see, you know, we're ranging over many orders of magnitude of KOW and over many orders of magnitude of Henry's law, which is kind of the point. I want you to see the difference between these 4 different types of chemicals. So the equations here for coming up with the percent in air and water are based on, I calculated the denominator, which, you know, is for the all 3 phases are present in the denominator, right? So I calculated the denominator separately here just to make my formulas a little bit less complicated. And now through the magic of television, I bring you these formulas. So the total mass in the system is volume of air times so it's the mass in the water, right? VACA times the mass in the water, VWCW, times the mass in the oil, V oil, C oil. So the trick here is that you have 3 phases, right? So if I want to calculate the percent in the air, that is the mass in the air over the total mass. The mass in the air is VACA. The total mass is the sum of these 3. And then we do our magic trick of dividing everything through by CW. So this CW cancels out, and this becomes, top one here becomes Henry's law, and this becomes KOW. So that's how we get this equation. And then by analogy, if we want to do the mass in the octanol, this would be the octanol phase in the denominator, VOKOW, and the denominator stays the same, right? Because the denominator is always these 3 phases. So that's why I calculated the denominator here. This is just to make the formulas a little bit easier in Excel. You can do it however you want. I have the volumes here, and so here's my formula. So this is the percent in air, so it's Henry's law times the amount of air here divided by the denominator. Okay, so it makes the formulas quite straightforward. Do that calculation for all of the different phases. And then I plotted it, you know, by going to insert. And I used a bar chart here, and I used a stack bar, you know, did it like that. So So that's how you get this bar chart. And the point is, okay, phenanthrene is kind of split between the sludge and the water. Tylenol is virtually 100% in the water because you can see it has a low KOW value. Here's Tylenol. KOW is only 0.27. Log KOW is only 0.27. Chloroform is mostly in the air because it has a high Henry's Law constant, of 0.2, dimensionless. And then TCDD is almost entirely in the sludge. So I'm trying to get you to see, I'm not making this stuff up. This is really how wastewater treatment plants work. Most of the chloroform that gets generated is going to volatilize away, but some of it will end up in the receiving water. Many drugs, including antibiotics, are pretty polar, so they stay in the aqueous phase and they just flush right through the wastewater treatment plant. This is part of the problem. Wastewater treatment plants are not designed to handle things like this. It's really only through luck that wastewater treatment plants do such a good job of removing big hydrophobic molecules like dioxins, PCBs, brominated flame retardants. Those big molecules end up in the sludge, but of course that doesn't mean you're off the hook. You still have to do something with the sludge. So that's the point of this. And then I asked some other questions down here. This turned out to be not a very good midterm exam. I will probably never ask this question again, or at least not in this format, because I think people were really confused by the wording. But the more important part is for you to look at this tab here, which is questions 2 and 3. And here I basically do the math to calculate this table, right? So this is you can think of this as a map of the world. Here's log KOW and here's log KAW, Henry's Law. For every chemical in the world, you can look it up and say, okay, a log KOW of 7, Henry's Law constant of -6, it's going to end up here in this region, and so it's going to be in the sludge. Right, and so you can really rapidly, easily figure out how your chemical is going to behave by drawing this kind of plot. And in the spreadsheet here, I do the math to make this plot happen. And I also, did some fancy coloring here just to show you if you want to see it that way. But I find this plot to be much more useful. So in your homework, you're asked to do these calculations and then ask whether they fit with this kind of plot that we had drawn. Is your chemical, if your chemical is over here with a log KOW of 9 and a low Henry's Law constant, did you actually calculate that it all ended up in the sludge? And that's my husband making noise in the background while I'm trying to record. All right, so let me know if you have questions. I'm always here to help. Talk to you later.